What we're going to be doing here is doing a quick chemical naming review. In this video, I'm going to review how to name ionic compounds, how to name molecular compounds, how to name acids, and how to name hydrates. So let's start here with ionic compounds. Now, you can recognize an ionic compound because it's either going to contain a metal ion or it's going to start with NH4. So just a reminder here, on your periodic table, there's this solid dark line here that's called the staircase line. And anything to the left of this is going to be a metal ion. So if you have a compound that has any one of these, like Na, which is sodium, or Sc, which is scandium, those are metals. And that tells you that you have an ionic compound. The one exception to this is NH4. NH4 is a polyatomic ion, which we're going to get into what those are in just a minute. But basically, NH4, when you put it together as a compound, it's has a +1 charge. So because it has a +1, it's going to be acting like those metals, which also have positive charges. So there's 3 scenarios we need to consider when we're naming ionic compounds. So the first is going to be just a binary compound, which just has 2 elements, one metal and one nonmetal. What we do when we're naming a binary ionic compound is we just give it the name of the metal as is. So if you have calcium, you're just going to write calcium. If you have zinc, you're just going to write zinc. The nonmetal, on the other hand, we call that the anion, is going to be, we're going to basically change the ending of that. So for example, if you have oxygen, which is a nonmetal, when it forms an ionic compound, we call that oxide. Or if we have fluorine, which is another nonmetal on the right side of your periodic table, we're going to change the ending of that to fluoride. Now, the other thing you're going to run across is what's called a multivalent metal. And multivalent metals are in the transition elements. And what happens is they can have more than one possible charge. Essentially, what we have to do when this happens is you have to tell me which charge you're using. On your periodic table, the first charge is going to be the more common one, but if we're using the first charge or the second charge, that needs to be indicated. So what we do is we indicate that with brackets after the name of the metal. So for example, iron 2 oxide is telling me that I have iron with a 2+ charge. Now, there's kind of an older notation that you may run into where they're saying something instead of iron 2 oxide, they'll be saying ferric or ferrous, something like that. That's an old notation, but just so you know that that is basically doing the same thing. It's telling you what charge that we're dealing with. And then the last situation you're going to run into with polyatomic ions is when you don't just have 2 elements, you have multiple elements. So, for example, at the top of your periodic table, there's often a table like this one, which is the table of common polyatomic ions. So these are ions, but instead of just having one element in them, they basically have a group of elements that are kind of together in a complex. So for example, remember I mentioned ammonium earlier? There it is on the second one there, NH4+. And then what we have to do is we have to use this table in our naming. So in order to do that, you basically also have to change a little bit the way you're writing the name of the compound. So what we're going to do now is we're going to go through a bit more detailed examples of all of those different scenarios, starting with just basic binary ionic compounds. So the first thing that we're going to do is we're going to go over how to write chemical formulas for the following. So aluminum sulfide. What I would do is if I'm going to write a chemical formula for this, is I would first pull out my periodic table and I would look up these elements on the periodic table. So on the periodic table that I just pulled up there, you'll see number 13 here, atomic number 13. That's aluminum. And 16 is sulfur, which we're calling sulfide because, of course, it's in an ionic compound. So the first thing you're going to want to do is you're going to want to look up the charges here. So aluminum is a +3 on this. Sulfur doesn't have it on this periodic table, but just like oxygen above it, sulfur is always going to be a -2. So those are the charges that are formed in this ionic compound. Now, some people, when they teach you how to write a chemical formula, are going to go through something called the crisscross rule. So what you do with the crisscross rule is you basically take the charge of the one element, so the charge of sulfur, and it becomes the subscript of aluminum, and then the charge of aluminum becomes the subscript of sulfur. So the chemical formula for aluminum sulfide is Al2S3. But I want to go into detail in a minute why this happens. Basically, what happens when an ionic compound forms is this metal is going to be giving up electrons to be more stable, and the non-metal is going to be taking on electrons to be more stable. So what we have to do to form this ionic compound is we have to balance out those electrons being given away and taken, given away and then taken in, because everything there has to balance out. So aluminum having a +3 charge here, basically if I use 2 of these aluminums, that's all together going to add up to give me a +6. Whereas sulfur, if I have 3 of them, that's going to give me a -6. The +6 and the -6 are essentially going to cancel each other out, or all of the electrons that come from the metal are going to the non-metal. So it's the simplest ratio that you can use to transfer those electrons. So that's why we have a ratio of 2 aluminum to 3 sulfide. Sodium oxide, we're going to do the same idea here. Sodium has a +1 charge. Oxygen has a -2 charge. If I want to balance out those charges, what I would need is 2 sodium, because if I have 2 sodium, that's going to be +1 and +1, which will give me a +2. And if I go +2 and -2 and add those together, that's going to cancel out. So the formula for sodium oxide would be Na2O. Now, if you are going to write chemical names for basic binary ionic compounds, what you're going to do is you're going to find this symbol on the periodic table. So Ca, you would want to look on your periodic table until you find it. And I've kind of pulled it up here. You can see here the atomic number 20, Ca is calcium. And then on the other side of my periodic table, O of course stands for oxygen. So how I write the chemical name is I always start with the metal. So it's going to be calcium, and then oxygen I'm going to change to "ide", so it's calcium oxide. Magnesium, we're going to do the same thing. So that Mg stands for magnesium, and the O is oxygen again. So the name of Mg2O3 is magnesium oxide. So those are binary ionic compounds. What I want you to do right now is I want you to pause the video, and I've got a couple on the screen here, and I want you to try them. And then when you get them done, I want you to start the video again, and I'm going to throw the answers up here for you. So this is what you should have got for those chemical formulas. At the top here, you should have got K2S and ZnF2. And then in the bottom, the names of these two ionic compounds are strontium oxide and scandium sulfide. So the next scenario we're going to be taking a look at is multivalent metals, and that's when they can have more than one charge. So these are the examples that I'm going to do. Let's start with manganese 4 oxide. That IV is the Roman numeral for 4. So if you take a look at manganese on your periodic table, what you should see here is that there's a +2 or a +4 in the spot where the common charges go. Now, between those two, the 2 is the more common one, but what I've done is I've indicated what charge to use with that Roman numeral. So IV stands for 4, so what that means is that I'm going to use the +4 charge for the manganese. Now, oxygen has a -2 charge, so in order to balance those out, what I would need is 2 oxygens, because that would get me up to a -4, and -4 and +4 would cancel out. So the formula for manganese 4 oxide would be MnO2. Nickel 2 nitride is telling me that I have nickel with a +2 charge. Nitrogen has a -3 charge. So what we need to do is we need to figure out the lowest ratio of those two numbers, so our charges will balance out. So the lowest common multiple of 2 and 3 is 6. So what that means is I'm going to need 3 nickel and 2 nitrogen. So that formula is Ni3N2. Now, going down to the formulas and how do we write the names? What I would do is I would again go to my periodic table and I'd find what is CO. So if you look through your periodic table, you're going to go to atomic number 27, and that should tell you that CO is cobalt. And cobalt can either have a charge of +2 or +3. So how are we going to figure out what charge it has? Well, you have to look at the ratio written in the chemical formula. CO and then this O is oxygen tells me that I have a 1-to-1 ratio of these two. Well, because we know that oxygen has a -2 charge, what that's telling me, so oxygen over here has a -2. What that's telling me is we have to use the +2 charge of the cobalt because that's what we need to do to have a 1-to-1 ratio for those charges to cancel out. So what I would name that then is cobalt 2 oxide. The 2 there in Roman numerals is telling me that I'm using the 2+ charge. Cu3n, you're going to do the same thing. You're going to go to your periodic table, and if once you're done scanning, if you take a look at atomic number 29, Cu is copper, and copper can either be a +2 or a +1. So we have to decide, well, which one did we use? Well, if you go over here to nitrogen, nitrogen has a -3 charge. So if I've got 3 coppers, that means I must have been using the +1 charge, because 3 positive ones is going to get me to a +3. So this one right here is copper 1 nitride. So now I'm going to get you to do the same thing as before. I want you to pause this video, try these two for yourself, and then when you're done, you can start the video again, and I'm going to give you the solutions. So the solutions for these, vanadium 5 fluoride is going to be VF5, and it's a solid because ionic compounds are always solid unless they're in solution. And Au2O3, Au stands for gold, and because of the ratio of these two, we know that we have to have gold 3 oxide. So the next thing you're going to come across is polyatomic ions. Polyatomic ions you should recognize because either you're not going to find them on your periodic table or they're going to have a different ending. Like this first one here where it says sulfate. Well, all of the anions on the periodic table are going to end in I, like fluoride, bromide, oxide. Now, there's some polyatomic ions that end in I too, but you won't be able to find them in the non-metals. So that's how you know to look for the polyatomic ions. So at the top of your periodic table, you're going to find this table of common polyatomic ions. And once you know you have a polyatomic ion, what you're going to do is you're going to look up here until you locate which ion you're talking about. So sulfate is right over here on the third column. Sulfate is SO4 and it has a -2. Copper, this is one of the multivalent, like our last example. That 2 is telling me I'm using the +2 charge. So +2 and -2, those are the same charge. So what that means is we need a 1-to-1 ratio of those. So how I would write this formula is just CuSO4. And it's again solid because it's an ionic compound. Zinc cyanide, on the other hand, cyanide does have an IDE ending, but there's no cyan on the periodic table. So that's your cue to come look at the chart up here. cyanide's in the second column there, and what the formula for that is CN negative or a -1. Now, if you go to your periodic table, what you're going to see is that zinc has a +2 charge. So what that means is that we need two of those cyanide ions to balance it out. So the formula then is ZnCN2. Now, you might notice I put that CN2 in brackets. That's on purpose. Basically, if there's more than one polyatomic ion, you have to write it in brackets and then write your subscript after the brackets. And if I didn't do that, what it would look like is that I only have two nitrogen when I really want two of both the carbon and the nitrogen, which together form the cyanide. So you have to put brackets if you have more than one of the polyatomic ion. And my two down here that I'm going to write their names for, you can see I've got multiple of them. The entire polyatomic ion is in brackets. So looking at the two chemical formula below here, we're going to do the same thing. We're going to go and try and find the names of these. So Mg, you'll find on your periodic table, that's magnesium. CH3COO, you're going to take a look at your polyatomic ion charts and you're going to locate it above. So if you take a look here, it's just the first one on the list, that's acetate. So how we would write the name of this one right here is you're just going to write magnesium from the periodic table, and then you don't change the ending at all for polyatomic ions. You just write them as is, acetate. Now, this one, by the way, you'll notice that it has ethanoate in brackets. You could also, if you want, write magnesium ethanoate. There's basically two ways to refer to the naming of this polyatomic ion. And then the next one, Zn, if you look on your periodic table, is zinc. And then NO3 is right here in the middle. It's nitrate. So all we do to write the name is we write zinc nitrate. So I'm going to get you now to pause the video. And what I want you to do is try and come up with the formulas for the first two. And then the second two, I want you to come up with their names for the formulas that are given there. So here's the answers then for your practice questions. Sodium phosphate is Na3PO4. So we needed 3 sodium to balance that phosphate ion. Beryllium nitrite, and I'm actually just seeing here, I have an error. This is not NO3. This should have been NO2. So if you put NO2 there, that's actually correct. NO3 is nitrate. So this is Be, and then we needed 2 of these nitrites. So that's going to be NO2 instead of 3 there, and then there's 2 of those. And then copper 2 hydroxide and aluminum phosphate are the names of the two compounds below. Don't forget, you still need to do the multivalent thing if you have a multivalent metal in the transition metals there. So the next thing we're going to go through is how to name molecular compounds. Molecular compounds only contain nonmetals, which are the right of the staircase. They can actually form very complex compounds, and their naming rules can be a lot more in depth. But for now, we're just going to review how to name simple two-element molecular compounds, and we're also going to look out for some common names that you're going to come across. Now, as you go further in chemistry, you will learn some of those more complex naming conventions. Like, for example, if you take Chem 30, you're going to learn how to name organic compounds. But for now, this is all we need to know how to do. So, for molecular compounds, binary molecular compounds, so those are ones that are only composed of 2 atoms, are named according to prefixes to tell us how many that we are going to have of each of the atoms. So, for example, you've come across these before. Carbon dioxide is CO2. What this compound has in it, this di here is a prefix. And the prefixes you need to know are mono is 1, di is 2, tri is 3, tetra is 4, penta is 5, hexa is 6, hepta is 7, octa is 8, nona is 9, and deca is 10. We don't usually name too much beyond this, so those are the main ones to know, and if you run into something that's higher, well, I guess you'll just have to look it up. Now, that carbon dioxide, if you're looking at that di, you can see di is 2 here, so that O2 makes sense, right? But there's only one carbon. We don't often write a 1. And I didn't write monocarbon dioxide, and that's because just by convention, we only use mono if there's one of the second element, not if there's one of the first element. So basically, if I had one of the oxygen, I would write monoxide. But if there's one of the first element, carbon, I don't write monocarbon. So let's do a couple examples here. Sulfur hexafluoride. So sulfur, it doesn't tell us what prefix there is. So by default, we're going to go to there being 1 sulfur. Hexafluoride, hexa means 6, and fluoride is F. So the formula for sulfur hexafluoride is going to be SF6. Now, CO is the next one we're going to take a look at. C, if you look on your periodic table, is carbon, and O is oxygen. So carbon, because there's only one of those, but it's the first element, we're just going to write it as carbon. The second element here, oxygen, we're going to change the name to oxide, just sort of like what we were doing with ionic compounds. And there's only one of this one as well, so this is where we have to put the mono. So this is going to be carbon monoxide, which of course you should be familiar with because that's something, it's an emission from vehicles, but also it is dangerous for humans to breathe in. Your house actually might have a carbon monoxide detector just to make sure that you aren't having too much in your home. Sulfur hexafluoride, though, you're probably not as familiar with, but I've got a video here that can kind of show you a little bit what sulfur hexafluoride is. It's actually kind of a fun element. So take a look at this video and then we'll kind of get back to our naming after it.
I promise to show you something really cool as long as you promise not to try it at home, okay? Okay. Now, everyone wants to know why my voice sounds higher when I inhale helium.
My simple fact is that helium is 6 times less dense than air, which means sound waves travel through it much faster, which makes my voice sound much higher. Now, the same effect can be achieved in reverse if I inhale something like
Sulfur hexafluoride, which is 6 times denser than air. I inhale some of that,
and my voice gets really low, although somehow I'm still funny. It's scientific!
All right, so sulfur hexafluoride is kind of a fun compound. Obviously, you wouldn't want to inhale too much of it, but you can do a little bit, sort of like helium. It'll give you a low voice. Now, the other thing you might want to be aware of with molecular compounds is some common ones that you'll come across that don't quite follow our naming convention, but you're going to run into them because they're just so common. So one really simple one is water. Water is H2O, of course. We don't name that dihydrogen monoxide. We just call it water because, of course, it's one of the most common things that you'll come across. Hydrogen peroxide, you probably heard of as well. Maybe you put it on a cut at some point in your life. Hydrogen peroxide is H2O2. Peroxide is actually on your polyatomic ion chart sometimes, but hydrogen peroxide is named like that instead of dihydrogen dioxide. Ammonia is another one, NH3, it's a smelly substance. Glucose and sucrose, those are sugars that obviously you'll find a lot if you study biology. Methane is another one, methane gas. That's natural gas. We use it to heat our homes. CH4. Propane, you might use that in your barbecue. That's C3H8. Octane is a major component of the fuel in your car. That's C8H18. Methanol, that's a cleaning agent usually, but it's an alcohol. CH3OH. Ethanol is another alcohol. Sometimes it's used as a cleaning agent as well, but it's also the type of alcohol that you'll find in alcoholic beverages like beer or wine. And then hydrogen sulfide, if you ever worked in any sort of industry like the oil fields, you might have had to take an H2S Alive course. Hydrogen sulfide is a poisonous gas and it's produced in a lot of industrial processes. So it's very common to have to take a course just to know how to properly rescue yourself if you end up exposed to it. So those are some common molecular compounds. You should just kind of familiarize yourself with those so that if you run into them, you're not totally lost. So I'm going to pause the video here for a second and I want you to write chemical formula for the first compound there, phosphorus trihydride, and then for NH3, I want you to write the name. Okay, so what you should have put for phosphorus trihydride is PF3, and NH3 is ammonia. You might have put nitrogen trihydride, which is, of course, the correct naming convention way, but we would really just use ammonia, which is the common name for this. So the next thing we're going to talk about is how to name an acid, and then we're going to eventually get into hydrates as well. So acids you can recognize because they contain an acidic hydrogen ion. So they're always going to have hydrogen in them, and they're either going to be with a halogen, which is group 17 in your periodic table. So that's like chlorine, fluorine, bromine, those elements there. Or it's going to be a hydrogen paired with one of the polyatomic ions for your polyatomic ion charge. So the names for acid is based on whatever the anion, so that's the halogen or the polyatomic ion, whatever the ending is of that name. So if the anion name ends in ide, so that'll be any of the ones on your periodic table like fluoride, or some of the polyatomic ions like cyanide. What we do is we call hydroic. So basically that blank space there between the hydro and the ic, what we do is we insert the name of the anion there. And then we put acid at the end. So HF, for example, has fluoride in it, so we would call that hydrofluoric acid. Now, if the anion name ends in ate, the acid name is just ic acid, so it takes that hydro out. So phosphate, for example, H3PO4 contains phosphate. What we call that one is phosphoric acid. And then lastly, if the anion name ends in ite, then the acid is named an us instead of an ic acid. So NO2 is nitrite, so we call that nitrous acid. Let's do a few more examples here. HCl. What you would do is you would go and look on your periodic table and you would see that Cl is chlorine, which when it's an anion, we call it chloride. And that ending in ID, we're going to use the hydroic acid naming convention. So HCl is hydrochloric acid. I'm just inserting the chlor in the middle there. Now, this next one right here is a polyatomic ion, H2SO4. So you're going to grab your polyatomic ion chart and you're going to locate SO4. And you'll see it's right over here on the third column. SO4 is sulfate. So ending in 8 is your second rule. So that's going to be an ic acid. So this is sulfuric acid. Now, oxalic acid, that tells me that I'm dealing with an oxalate. So that's a polyatomic ion. If you look at your polyatomic ion chart, it's in the middle column right here, OOCC002 negative. And just like with ionic compounds, what you're going to have to do with the hydrogens is you're going to have add enough hydrogens to balance out the negative charge. So hydrogen has a +1 charge. Oxygen has a -2 charge. So what that means is that we would need 2 hydrogen to form oxalic acid. So sometimes you could see this written as H2 and then the entire polyatomic ion. But the better way to write oxalic acid itself is actually HOOCCOOH. Now, you might be wondering, why would I do that? I actually did add both hydrogens. They're right here on either end. But the reason that I do that is because that COOH group is special. It's what's called, excuse me, it's what's called, it's basically an organic acid. So that COOH is actually the structure of that organic acid. So when I write it like this, I'm actually writing it in a way that's more true to its structure. Now, HBr is a hydroic acid. So that tells me I'm dealing with bromide, which, like I said, could be a polyatomic ion, but in this case, it's not. Bromide is coming from the element bromine. So bromine has a -1 charge. So the formula for this one is HBr. So I'm going to have you pause the video right now, and the two at the bottom, I want you to try yourself. So HClO and sulfurous acid. So HClO is a polyatomic ion. It's in that first column there. So that's hypochlorite. So this would be hypochlorous acid. And then sulfurous acid, you would be dealing with sulfite, which is SO3 with a -2 charge. So you would need two hydrogens for it. So this is H2SO3, and I got an S there. That should have been a 2. So this is H2SO3, and AQ means aqueous, and that's just telling me that it's dissolved in water. Now, the other thing that you might come across is a hydrate. And basically what happens is some ionic compounds form a complex with water, and we call that a hydrate. So how we name these is the ionic part of this compound is named like any other ionic compound. But what we do is we put basically a prefix hydrate on the end to indicate that it's a hydrate and not just a regular ionic compound. And the prefix is going to tell me how many water molecules are contained. So for example, this one below here, CuSO4, what I would do is I would start just naming that CuSO4 as always. So Cu is copper, and copper can either be a +2 or a +1. SO4 is a polyatomic ion, that's sulfate, which is a -2. So the fact that I have a 1-to-1 ratio tells me that I'm using copper 2, not copper 1. So this is copper 2 sulfate. What I would do is I would just leave that as is, but on the end of it, I would add pentahydrate. Penta, of course, being the prefix for 5, and then hydrate tells me that I would have water. So this becomes copper 2 sulfate pentahydrate. Now, there is also another way that is sometimes used to name these hydrates. It's a little simpler in some way. Instead of going pentahydrate, I just say there's 5 water. So this could also be copper 2 sulfate 5 water. Both of those would be correct. You should be familiar with both of them. So I want you guys to try this one yourself. So pause this video. I want you to name this hydrate, and then you can start it up again, and I'll give you the solution. So what you should have had for this one is sodium carbonate decahydrate. So, a couple other things to be aware of. The first is molecular elements. Basically, some elements are so reactive that they actually don't like to exist as a single atom. So, they react with each other to form what's called a molecular element. So, the most common ones are the diatomic ones. So, that'll be nitrogen, oxygen, fluorine, chlorine, bromine, iodine, and hydrogen. Um, Basically, all of these like to form a complex of 2. So N2, O2, F2, Cl2, Br2, I2, and H2. Sometimes we call these the special 7. Basically, if you look at the periodic table, they form a 7 on the periodic table, except for hydrogen, which is kind of hanging out on its own. But you do have to have these memorized. Now, these other ones are sometimes, but not always. You will see them, but they're not always in a molecular state. So, phosphorus and sulfur. Phosphorus is often written as P4, sulfur written as S8. How I remember this is phosphorus has a party with 4 of its friends, whereas sulfur has a super party. It has 8 of its friends, double the size of phosphorus's party. So you do need to be aware of and have those memorized as well. Now, you might have noticed throughout this presentation that I was including states of matter on most of the compounds, and that you should get used to doing that as well. I just want to quickly review how do you figure out what these states of matter are. So elements, you're going to look at the key on your periodic table. Our periodic table does them by color. Other periodic tables do it sometimes by font. You just have to look. It'll tell you on the periodic table how it's telling you what the state of matter is. Ionic compounds, you're going to assume solid unless it tells you that they're dissolved in water, in which case you're going to put AQ, which means aqueous or dissolved in water. Molecular compounds are a little hard to predict. Either the question will tell you, unless it's like a common substance. So, for example, ethanol, that's a common alcohol. You should know that's a liquid. Carbon dioxide, you should know that's a gas. Water, depending on the temperature, I would expect you to know that water at room temperature is a liquid. And then the last thing you should know that is that acids are always aqueous. So at this point, I want you to go and try your practice questions. So there's a nomenclature assignment on your Brightspace, and then also there is the C2 daily quiz. One note about this quiz, valence. It mentions valence, which we didn't really talk about in the video, but basically in the context of ionic compounds, it's just asking you what the charge is on that ion that's being formed, either the cation or the anion. So, um, and if you have any questions, just feel the need to contact me.